Very good morning everyone. Today we will see the problem of design of RC member for combined bending, shear and torsion. Myself Dr. J. Savayaruban, Professor and Head, Department of Civil Engineering, Rohini College of Engineering and Technology. Design a reinforced concrete beam of cross section for the following data. The width of the beam is 300 mm, then effective depth is 800 mm, overall depth of the section is 850 mm, and characteristic compressive strength is 50 Newton per mm square, then tensile strength is 250 Newton per mm square, moment is equal to 200 kilonewton meter, then shear force V is equal to 100 kilonewton, Tu is equal to, that is torsional moment, is equal to 50 kilonewton meter. First we have to find out the equivalent shear. The equivalent shear is given by V is equal to Vu plus 1.6 into Tu by AB. So substitute the value. Already we know the value of Vu, that is 100 plus 1.6. Tu torsional moment is 50 divided by B 300 converted into meter 0.36. So that will be is equal to 366.67 kilonewton. Then we have to find out the value of tau VE. So tau VE is equal to VE divided by B into D. So tau VE is equal to 366.67 into 10 power 3 divided by 300 into 800. That will be is equal to 1.53 Newton per mm square. For a M15 concrete, that is tau C max, we will get it from the table 20 of IS 456 2000, get 2.5 Newton per mm square. Since the tensile reinforcement is not known at outset, therefore the minimum percentage of tension steel, that will be calculated by 100 AST by BD. So 100 into AST, that is 0.85 divided by F5, that will be equal to, you will get it 0.34 percentage. So that minimum percentage of tensile steel is 0.34 percentage. So using this one, we have to find out the tau C value. So tau C value you will get it from the design station from table number 19 of IS 456 2000. That value will get it 0.39 Newton per mm square. That is less than tau VE, that maximum shear stress. Hence both the longitudinal and transverse reinforcement shall be provided. Okay, next we have to find out the equivalent bending moment. So equivalent bending moment, as we know, MEL is equal to MU plus MT. So the MT value is given in the problem itself, that is 200. Then that MT we have to determine by this formula, that is Tu into 1 plus D by B divided by 1.7. So we know all the value, just substitute all the value here. 200 plus 50 into 1, D is 850, that overall depth, B is 300 divided by 1.7. We will get a value of 312.75 kilonewton meter. Since the MU is greater than MT, so no longitudinal reinforcement will be required on the compression flange. Next is we find the longitudinal reinforcement. So MEL, page number 96 of IS 456 2000. We will get it 0.75 Fy AST in D 1 minus AST Fy divided by BD into FCK. So substitute all the values here. MEL already we find out 312.75 into 10 power 6, that will be equal to 0.87 into 250 into AST into 800 into 1 minus AST into 250 divided by 300 into 800 into 15. So from that we will get a AST. So simplify this equation, finally we will get a AST values 2105.06 mm square. So provide 4 numbers of 28 mm diameter rods. So once again we have to find out that 100 AST by BD, that is a minimum reinforcement. So 4 numbers of pi by 4 into 28 square. We will get a value of percentages 1.03 percentage, that is greater than the AST minimum. So the tau C will be revised by, we will get it by the tau C value is equal to, from that this 1.03 we have to use that table number 19. Once again we have to take the value of tau C, that is 0.605 Newton per mm square. Next we have to find out the transverse reinforcement. So the transverse reinforcement given in the codal provision, AC is equal to Tu by SV divided by V1 D1 into 0.87 Fy plus Vu SV divided by 2.5 D1 into 0.87 Fy. So provide side and top cover of 30 mm and two numbers of 10 mm diameter bar at the top. So B1 we have to find out, that is without the beam is we already know 300 minus cover 30 minus 30 into minus that longitudinal reinforcement divided by 2 minus longitudinal reinforcement divided by 2. So that will be equal to 212 mm. So B1 is equal to 212 mm. B1 nothing that width of the reinforcement in the x direction. Then D1 we have to find out. So that effective depth we know 800 minus 30 is a cover minus that reinforcement is 10 by 2, that will be equal to 765 mm. So next we have to provide the stirrups. So assuming 8 mm 2-legged stirrups. So from that we have to find out AC. So 2-legged stirrups 2 into pi by 4 into d square will get 100.53 mm square. So substituting the values in the above equation will get, that is ASV 100.53 is equal to 50 into 10 power 6 into SV divided by 212 into 765 into 0.87 into 250 plus 100 into 1000 SV divided by 2.5 into 765 into 0.87 into 250. So the SV, by simplifying this equation, finally we get the value of spacing of stirrups is equal to 60.64. So if we have to use 8 mm 2-leg stirrups at 60 mm center to center. The arrangement of reinforcement is given in the figure. So this is a arrangement. The size is given 8-leg 2-leg stirrup for 60 center to center. The clear cover is 30 bottom and top. So this is a 4 numbers of 10 mm, also the 4 numbers of 28 mm main reinforcement. This is the figure shows the arrangement of reinforcement. So this is about combined shear and torsion problem. Thank you so much.